Good morning friends, welcome to Active Learning video lecture organized by Gujarat Technological University at Bisec. Myself Silavat Mohammed Rahish from Gandhinagar Institute of Technology, and today we are going to learn about elements of electrical engineering, in which we will cover the topic magnetic circuit and electromagnetic induction. This is our topic, magnetic circuit and electromagnetic induction. We will cover magnetic circuits, then we will have idea what is magnet, what is magnetic field, what is magnetic flux, then we will see Coulomb's law. After that we will see what is permeability, then we are going to see the classification of magnetic materials. After that we will have an idea of magnetic density, then we will have an idea of magnetic intensity. After that we will find the relation between magnetic density B and magnetic intensity H. Then we will see what is reluctance, and finally we will have examples based on magnetic circuits. Our second portion is electromagnetic induction, in which we are going to see EMF. After that we will have an idea of Faraday's law. Then we will see what is Lenz's law. After that we will see the right hand rule, the Fleming's right hand rule. Then we will see the types of induced EMF. After that we will have dynamically induced EMF, which is the type of induced EMF. Then the second type of induced EMF is statically induced EMF. Then we will see what is self-induction and what is mutual induction. And finally we are going to see the applications of electromagnetic induction. So magnet. What is magnet? Friends, we already played with magnet in our childhood, but we don't know the application of magnet in our household appliances. So magnet is nothing but basically any object that attracts iron and which when freely suspended points towards the poles of the earth is called a magnet. Like electric charge, magnetic poles are there. The materials which are attracted by a magnet are called magnetic materials. Like iron is a magnetic material which is attracted by a magnet. When a magnet is freely suspended, the end which points towards the Earth's north pole is called north pole, and the end which points towards Earth's south pole is called south pole. So basically there are two poles in magnet, north pole and south pole. In electrical field we have a charge called positive charge and negative charge. Same in magnetic field we have two poles called north pole and south pole. After that, what is magnetic field? So friends, in electrical field we saw that there are electrical field lines in electrical field. So therefore in magnetic field same, the electrical field lines and the magnetic field lines are there. When a magnet is placed near another magnet, it experiences a force. The force can be repulsion force or attraction force. The region around a magnet in which another magnet or magnetic materials experience a force is called a magnetic field. So same like electrical field, a magnet has its magnetic field, in which it has some magnetic field lines like electrical field lines. Now what is lines of force? So here we have two magnets in which north pole and south poles are given. Two magnets are placed near each other so that the south pole of one magnet is near to the north pole of another magnet, and the field lines are there. Now what is magnetic flux? So we saw that electric flux in electric circuit, same in magnetic circuit we have magnetic flux. If some area is given and magnetic field lines are passing through the area, so that the total number of magnetic flux lines passing through the area is known as the magnetic flux. Now what is magnetomotive force? Magnetomotive force is like electromotive force. In electric field we have electromotive force, which is very useful to pass the current into any conductor. So the magnetic motive force is a force which is used to produce the flux in any magnetic circuit. Without magnetomotive force we cannot have magnetic flux. Here we have a magnetic circuit in which the area is given and the current is flowing through the circuit. Now we will see the characteristics of magnetic field lines. We saw the characteristics of electrical field lines, same in magnetic field. The first characteristics is the magnetic field lines always emerge from the N pole and enter into S pole. In electrical field we saw that the electrical field lines always originate from positive charge and end up to the negative charge. So in magnetic field, the magnetic field lines always emerge from the N pole, which is north pole, and enter into the south pole. The second characteristics is that they form closed loop. It means the magnetic field lines go from the N pole to the south pole, and after that it forms a loop and come again to the north pole. After that, the third characteristics is they never cross or touch each other. Like electrical field lines, electrical field lines also do not cross or touch each other. And the fourth characteristics is that lines of force having the same direction repel each other, while those having opposite direction attract each other. It means that the same poles will repel each other, and if the unlike poles are there, then they will attract each other. Here we can see Coulomb's law. We saw the fundamental laws of electric field. Here we can see the fundamental laws like Coulomb's law in magnetic field. It says that like poles repel each other, whereas unlike poles attract each other. So friends, in first figure you can see that the north pole and south pole are nearby each other. So there will be attraction between these two magnets. And in another figure we can see that the north pole is nearby the north pole of another magnet, so that the like poles are near each other. It means that they will find repulsion force between them too. Here we can also see that in first figure the north pole is near to the north pole and the south pole is near to the south pole. It means that there will be repulsion force between these two magnets. It means that the first magnet will repel the another magnet. But in the second figure we can see that the south pole is near to the north pole, and another side the north pole of first magnet is near to the south pole of another magnet. It means that unlike poles are nearby each other, so they will find attraction force between them, and the first magnet will attract another magnet and vice versa. That was the first law of Coulomb. Now we are going to see the second law of Coulomb. So the second law says that the force between two poles is directly proportional to their pole strength and inversely proportional to the distance between their centers. See, we have seen electrical field and in which the two charges are there, and the law says that the force between two charges are proportional to the product of the charges. So same in the magnetic field, the force between two poles is directly proportional to the product M1 and M2, where M1 and M2 are the poles. The D is the distance between the pole, so that the force between the poles is inversely proportional to the square of the distance between two poles. So then we can put a constant F is equal to K M1 M2 by D square. K is the constant. So we can have the value of K. K is equal to 1 by 4 pi mu 0 into mu r, where mu 0 is the absolute permeability and mu r is the relative permeability. Later we are going to see what is permeability. Now finally we can get F is equal to M1 into M2, which is the product of the two poles, by 4 pi into mu 0 mu r d square. and the unit of the force is newtons. So if we are taking a medium, then F will be equal to m1 m2 by 4 pi mu 0 mu r into d square. But if we are taking air, then the F, the force, will be equal to m1 m2 by 4 pi mu 0 into d square, because mu r, which is the relative permeability for air, will be 1. Now friends, the two charges are there. So in electrical field and magnetic field there is a difference. The difference is that if we take two charges, positive charge and negative charge, so the two charges can be isolated, but the two s and n poles in magnetic field cannot be separated. It means that we cannot have south pole and north pole. It always have as a dipole. No matter how many times you cut, if you cut the magnet, so that it will again act as a dipole. It means if the south pole is there and if you are cutting the magnet, then the second end of the magnet will behave as north pole, and if north pole is there, then the second pole will behave as south pole. Here we can again see that if we cut the magnet, then it will again act as dipole. So the single isolated pole cannot be exist. Now what is permeability? We saw in Coulomb's law that F is proportional to m1 m2 by d square, and where we put the constant k is equal to 1 by 4 pi mu 0 into mu r. So now we can have permeability. Friends, we seen that the conductor like aluminium can pass the current through them very easily because they are having great permittivity, or we can say that they are having great conductivity, therefore they are conductor. So in magnetic field, permeability is that thing which easily allow the more magnetic flux to be produced. It means that in electric field the conductors are there like aluminium, copper, which allow the current to pass through them because they are having more permittivity. And in magnetic field, permeability is like permittivity. So if the permeability of a material is high, then it will produce more magnetic flux, and if the permeability of material is low, then it will produce low magnetic flux and it will generate very easy magnet, and if the permeability high, then it will generate strong magnet. After that, we can see that the permeability of air is very poor, so it is taken as a reference. The permeability of any material is denoted by mu, but when the permeability is compared with air, it shows the relative permeability. So that we have a relation, relative permeability is equal to absolute permeability by permeability of air. It means mu r is equal to mu by mu 0. Now based on the permeability, we can classify the magnetic materials. Basically there are three kinds of magnetic materials. The first magnetic materials is ferromagnetic materials. The materials whose relative permeability is very high are called the ferromagnetic materials. It means that the ferromagnetic materials can produce high amount of magnetic flux because the relative permeability is very high. The examples of ferromagnetic materials are iron, steel, cobalt. Such materials can be used to make strong magnets. As I said earlier, if the permeability or relative permeability of a material is high, then it can be used to make strong magnet because they are strongly attracted by a magnet. The second type comes, which is paramagnetic material. The materials having relative permeability equal to 1 or slightly more than 1. It means that the permeability or relative permeability of paramagnetic materials is between 1 to 10 are called the paramagnetic materials. It means that it will attract the magnet but not that much strongly attract the magnet as the ferromagnetic materials attract. The examples of paramagnetic materials are platinum, aluminium, etc. These materials are attracted by a magnet but not strongly because the permeability is not that much as ferromagnetic materials, so that these paramagnetic materials will be attracted by a magnet but not very strongly. The third type comes as diamagnetic materials. The materials having their relative permeability less than 1 are called the diamagnetic materials. It means that the relative permeability will be less than 1 and they will be repelled by a magnet. The examples of diamagnetic materials are zinc, bismuth, sulfur, etc. Because the relative permeability of these materials are very low, so these materials are actually repelled by a magnet. So basically there are three kinds of magnetic materials: ferromagnetic materials, diamagnetic materials and paramagnetic materials. And now we can find the difference between these three materials, that the relative permeability will be high and then less. Now we are going to see the direction of magnetic field. Here in first figure we can see that there is a conductor and a hand is grasped around the conductor. Suppose we take a direction of that conductor outwards, it means that if we suppose that the direction of current is upward, then the direction of the fingers will give us the direction of magnetic field. It means, friend, here we can see that the direction of current I is upward, so that the fingers will give us the direction of magnetic field. It means that if we take a plain paper and we have a direction of conductor upwards, then